Okay. So at this point, we have a bunch of tests, right? We have a bunch of tests to use on series. We have the. So let me sort of sketch out some general rules of when to use tests. General rules. Okay. General rules on when to use the tests. Okay. So first off, use the root test only if, of course, powers, exponents are involved. Second, the ratio test is used if they are for factorials or powers and factorials. Okay. Third, and further, these guys don't use for rational functions. Don't use them if you see rational functions. Okay. Comparison and limit comparison are used for rational functions. And fourth, the integral test is used if you see a function that you can integrate. Okay, so so for example, right, if I give you something like this, 1 over k, natural log of k to the 1/2, k from 2 to infinity. Okay, you see something like this, what do you think? Are you going to use the root test? No. Are you going to use the ratio test? No. You use comparison? Right. What are you going to use? You're going to use the integral test, right? Because you see that this is, this is a guy that this is something that you can integrate using U substitution, right? If you see something like this, k over k plus 100 to the k from 1 to infinity, what would you say about this? What's your immediate reaction to this? Maybe the root test, but you see what happens when you use the root test, you're going to end up with 1 actually. This was a trick. This is a trick question. What happens as k goes to infinity for this one? You're actually going to end up with Actually, so I'm not sure, actually. What do you use for this one? Maybe use the ratio test. I'm not sure. Let's try it. The limit of k plus 1 we have k plus 100 over k. That's going to be oh, yeah, actually, so I'm sorry. This is a trick question, right? So think like this. If we have 100 plus k over k to the k, what does that turn into? You're going to get 1 plus 100 over k to the k, right? And as k goes to infinity, what does that turn into? That turns into e to the 100. Right? So these terms, what happens to these terms? These terms eventually turn into 1 over e to the 100. Right? The limit of the sequence of the terms is actually going to be 1 over e to the 100, which is not 0. Right? It's not 0. So what do you know? That the series diverges. Right? So it diverges. Yeah, I'm not sure why I put that one in there. Okay. If you see something like k factorial over k squared, what are you going to use? Ratio test, right? Because you see the factorial. Right? Whenever you see the factorial, you know that ratio is probably your only thing to do. What about natural log of k over k squared? Actually, it's not completely obvious. Oh, no, it is obvious. Is it obvious? Smaller than. Now let me change this. Let me look at this. Over k cubed. What would you do in this case? You don't look at the rules, but just look at it directly. Think like what could you do when all else fails? Go back to the more basic tests. So, right, this is basically you're going to compare against 1 over k squared. Right, you know that natural log is smaller than k, so this thing is controlled by k over k cubed, right? Which converges, right, by the p, since p is bigger than 1. Right, so comparison, natural log of k is small over k cubed is smaller than k over k cubed. 1 over k squared converges. So natural log of k over k cubed converges. Okay. Last one. summation 1 over root k cubed minus 1. What would you do with that one? Comparison? Okay, comparison against what? Yeah, you could compare it. You could compare. So you could do limit comparison. Say limit comparison against 1 over k to the 3/2. Right. The square root of k cubed. Right. In the limit. Right. In the limit of this over this is going to be 1, right? So you know that if this one converges, this one converges, right? This one converges, they converge, either they both converge or they both diverge. And since you know this one converges, you know that this one converges. Okay, so that's it for these for tests for non-negative series. Now we're going to move to something a little bit more general. So let's see, please close your computer. Okay, so. Okay, so suppose you have a series that is not non-negative. Okay, right? You have some series, you know, it has negative numbers in it. For example, summation -1 to the n over n squared. -1 to the n over n squared, right? So you have -1 plus 1/2 squared minus 1/3 squared plus 1/4 squared minus 1/5 squared plus minus, etc. Okay. So you have right, all the tests we had before, you had to have non-negative numbers, right? But now we have some negative numbers. What do you do? Okay. Fortunately, there's one very big trick, okay? One powerful observation. It's this. If the sum of the absolute values converges, then the sum of the original series converges. Okay, if the sum of the absolute values converges, then the sum of the original guy converges. Okay, and we have a way of, there's a terminology for this. If the sum of the absolute values converges, we say that the series converges absolutely. Converges absolutely. So what this is saying, using this new language, is that if you converge absolutely, then you converge. Okay, so here is, if we look at this series, you say, well, look, if I take absolute values of it, well, what happens? If I take absolute values of this, if I take the sum of the absolute values, does this converge? Yeah, right, because it's n squared, right? So I know that this is gonna converge. Okay, so this series of, all this has some minus signs in it that maybe bother me a little bit, but then I remember, oh look, if I take the absolute value, it converges. So that means that this thing also converges. Okay, so if the absolute value converges, then the original guy converges. Okay. Here's the explanation. A sub n lies between the absolute value and the negative absolute value. Right? So 0 is less than absolute value of n plus a sub n is less than 2 absolute value of a sub n. Right? Everybody see that? I just added the absolute value of a sub n all the way through. Right? So everybody okay with that? Everybody okay with that? Okay. It's clear, right? A sub n, any number lies between its absolute value and its negative absolute value. Right? And then I just added absolute value of a sub n all the way through. Right? I get 2 absolute value of a sub n. I get a sub n plus the absolute value of a sub n. I get a sub n, absolute value of a sub n minus absolute value of a sub n, that's 0. So just adding the same number all the way through, right? Okay. So if this thing converges, then this thing converges by basic comparison. Okay, but then summation a sub n, since summation a sub n equals summation a sub n plus minus summation a sub n, we see that summation a sub n also converges. Okay, so this is an explanation, but I find this explanation sort of unsatisfying. If you don't get it, I don't care too much if you don't get this explanation. Okay, but let me run through it again. Okay, we're trying to see that absolute convergence implies that you converge. We're trying to see that if your sum of absolute values converges, then the sum of your original series converges. You say, okay, well, let's look. We make this observation. First, you observe that the normal values lie between the absolute value and negative the absolute value. You add the absolute value all the way through, and you get this thing. get this statement. Okay. Now, if the sum of the absolute values converges, then certainly the sum of twice the absolute value converges. But that would mean that the sum of the smaller guys converges, right? That's the basic comparison test, right? If the sum of the bigger guy converges, then some of the smaller guy converges. So if these guys converge, then these guys are going to converge. Okay, but then you observe, you say, well, look, the sum of the a sub n is actually the sum of this thing minus the sum of this thing, right? Right, which is a convergent series minus a convergent series, right? And so this is just a convergent series minus a convergent series, and so it's going to give you some number. So it's going to converge to. Okay. Okay. So this is a big trick, right? This is a really useful trick. What you say is that, well, whenever I have some series that has some negative numbers in it, I'm just going to put absolute values on it and see if it converges, right? If that does, then I know it converges. Okay. But sometimes that doesn't help you. Okay. Sometimes that will make you miss the convergence of some series. So warning. There are series which converge, but not absolutely. Okay, here's an example, and we'll explain it in a second. This is something called the alternating harmonic series. Alternating harmonic series. Okay. What happens if you take somebody gives you this and says, does this converge? And you just say, oh, I'm going to just take the absolute values of it. Okay. What happens when you take the absolute values? You get 1 over n, which converges? Diverges, right? It diverges. So, the absolute values don't converge. But in fact, the original series actually converges. Though the absolute value doesn't. Okay. So, absolute convergence implies convergence, but convergence doesn't imply absolute convergence. Okay. This thing converges, but it doesn't absolutely converge. Okay. So just because the absolute values don't converge doesn't mean that the series doesn't converge. Okay, it could still converge. Okay, so the way to think about it is that if these guys are the convergent series, then the absolute convergent guys are some subset of that, right? So if you're absolutely convergent, then you're convergent. But if you're convergent, doesn't mean that you're absolutely convergent, right? The absolutely convergent guys are special. Okay, these guys on the outside are called conditionally convergent. It just means convergent, but not absolutely. So, okay. So, we're going to talk about this alternating test, alternating series here. So here's the theorem called the alternating series test. Alternating series test. Okay, maybe I should just say alternating series condition. It's not really a test. So, let A sub n be a positive sequence. Okay. If the A sub n are non-increasing and the A sub n go to 0, then summation -1 to the n A sub n converges. Okay, so here's the example, right? The alternating. The alternating harmonic series. Okay, alternating harmonic series, right? These guys are your A sub n, right? They're all positive. They're decreasing. And they go to 0, right? Positive, decreasing, go to 0. So that tells you that -1 to the n times 1 over n converges. Okay, even though the absolute value doesn't converge. Okay. Another example, -1 to the n, 1 over n squared. Again, right, you have something that's going to 0, right, something that's decreasing to 0, and they're alternating in sign, right? So again, this thing converges. Why is this a dumb thing to say? Why is this a dumb thing to say? What's dumb about me saying this? Why is it, I'm going to say it this way, why is it redundant for me to say that this series converges? Or let me ask it this way, did we know this already without this test? Yeah, we knew this already, right? Because you just take the absolute values, and then the absolute values converges. Absolute convergence implies convergence. We knew this already. There's no need for me to say this, right? Right? Right, because we take the absolute value, we get summation 1 over n squared. We already know that converges, right? So we knew that this thing converged already. We didn't need to use the alternating series test, right? Okay. Okay. Another one, -1 to the n, 1 over n to the p, where p is some positive number, any positive number. What does the alternating series test say about this? alternating series test says what? It converges, right? Because this 1 over n to the p, p could be very tiny, right? P could be 0.00000001, right? But as n goes to infinity, this goes to 0. In fact, it decreases to 0, right? Right? This is interesting, right? Because this also converges, right? Even though, if we look at the absolute value, very much does not converge, right? Remember, the border is 1, right? Once we get past 1, the absolute values are not going to converge at all. But if it's an alternating series, then even if you have some sort of tiny exponent, as long as it's positive, you're going to converge. Okay. This is kind of cool. So let me see if I can give you a sense of why this happens. Why does this happen? Why does this work? Okay, so think like this. Okay, so let's say that our series is A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus minus, etc., etc. Okay, so if we take the partial sum, let's say that this is 0, okay, and we're going to add on A1. So the first partial sum is A1, right? S1 is A1. S2 is A1 minus A2, right? A1 minus A2, well, that's going to bring me back, but it's not going to get me all the way to 0, right? Because these are decreasing terms, right? So here is S1, and here is S2. Okay. Now, S3 is going to be A1 minus A2 plus A3, but it's not going to get me all the way back to A1 because again these are decreasing terms, right? So S3. Or maybe it could get me to A1, but it's not going to get me farther than A1 because I said it's non-increasing. So let's just pretend that they're decreasing, okay, just for the picture. Okay. And so what do you see happens, right? Then you come back here to S4, S5, S6, right, etc., right? S7, S8, right? And what you see is that the even guys form an increasing sequence, and then the odd guys form a decreasing sequence, right? So just look at the picture. Right? The even guys, S2m from m equals 1 to infinity, is an increasing sequence. S2m plus 1, the odd guys, is a decreasing sequence. Okay. Okay. Further, S2m is bounded above by A1. Right? S2m, you see these guys, A1 is bigger than all of them, right? A1 is bigger than all the partial sums in particular, right? So what does that tell you? You've got a bounded increasing sequence. So what? Maybe you've forgotten. Try to remember by tomorrow. You've got a bounded sequence and it's increasing. You've got a bound and you've got an increasing sequence. So what? converges. Right? So monotonic sequence theorem says that S2M converges to some number. Right? Converges to some L. Okay. But notice S2M plus 1 is S2M minus A2M plus 1. Or maybe it's plus, sorry, plus A2M plus 1. Right? So the limit of S2M plus 1 as m goes to infinity is L plus the limit of A2M plus 1 as m goes to infinity.